Today we're going to read from the April 1987 Byte magazine release called Instruction Set Strategies. Also in this particular release they're going to have BICS coverage of IBM, Amiga, Atari ST, Pascals, and Basics. BICS stands for the Byte Information Exchange. It's a worldwide low-cost online information service featuring industry news, downloadable software, powerful electronic mail, previews of upcoming Byte articles, the full text of published issues of Byte, etc. It's funny, to subscribe via modem, it says you need to set your communication software to full duplex 7 bits, even parity, one-stop bit. Then call this number, 1-800-225-4129. Once you've called the number, hit the enter return key and enter BIX when asked to log in. Then enter bix.vil, which is spelled VILLE, when asked for a name, for current fees and more information, and then they give you a number. So that's what a BICS is. Anyone new to Byte magazine, you'll see this quite a bit. So let's get to reading. Instruction Set Strategies. Here's the wonderful advertisements Byte is known for. One of my takeaways is back then the advertisements were significantly more informative, like you can actually learn stuff from them. And the language they choose to go with always cracks me up. Anyone and everyone who routinely works with equations needs Eureka, the solver. X plus exponent of x equals 10 solved instantly instead of eventually. And you get all this power for $99.95. So we have turbo everything here. Turbo Prolog, Pascal, Basic, C. We'll skip over the contents page. 1987 we have a senior vice president publisher named Harry Brown. The editor-in-chief Philip Lemons. Over here, Highwire starts the job that Smart Work finishes. Introducing Highwire. WinTech Smart Work is used by thousands of engineers to design printed circuit boards. I think this is a pretty cool graphic, right? The monitor screen. This guy's hand has some schematics written in cool 80s synthwave-like artwork. Here's the editorial section. Open systems with the March introduction of the Macintosh II, the Open Mac, and the February introduction of the Commodore A2000, the Open Amiga, the trend toward open, flexible personal computers has become dominant once again. Atari has announced that it will be opening its ST systems as well, since the Apple II world and the IBM PC world have long had open architectures. The entire industry seems to recognize once again the need to let users upgrade their systems and adapt them for different applications. It is much easier to build in flexibility than to have 20/20 foresight about every owner's future needs. And here's some technical details that I really like. The Macintosh II deserves praise for more than its openness. The CPU is a 6820, and every machine contains a 6881 floating point processor as well. A memory management unit is optional. The NU bus is a full 32-bit bus designed to facilitate use of additional processor cards. The graphics controller has unsurpassed flexibility. The standard I/O connectors will meet most people's needs. Backward compatibility with the Macintosh and the Macintosh Plus is high. What does that mean, backward compatibility is high? Like most things are backward compatible? Is that what they're saying there? The Macintosh II is the most powerful standard equipment of any personal computer. It has no 640K byte barrier to worry about and no shortage of sockets for memory. The Macintosh SE, with its one expansion slot, room for multiple internal disk drives, and other changes for somewhat faster operation, is a nice enhancement of the Macintosh Plus. Both machines have the superb Macintosh user interface. Now you'll also see I brought up this MOSI protocol. I don't know much about this at all, but they make mention of it over here under the BICS specials. So BICS users have the advantage of this month being able to join a new conference called BICS.Special. They talk a bunch about getting access to special articles. But over here, Jim Mooney, a member of the IAAA working group who's working on this standard 855-1985. This guy, in one of the articles I am interested in reading, will give us a thorough overview of the MOSI standard. And then Michael Carrion here tells us how to build a real-time clock for the Commodore Amiga for less than $25. Over here, the bonus electronic article, they say this issue of Byte introduces a new service to extend and complement our coverage. In addition to the articles published in the magazine, will regularly publish related articles on BICS. Such articles will not appear in the table of contents at the beginning of Byte, but they will be listed in the table of contents for the section to which they are related. It will also be noted that they are available through BICS rather than in print. Our first such bonus electronic article supplements this month's theme section on instruction set strategies. The related article available on BICS covers the Acorn RISC machine and was written by James J. Farrell III and John F. Stockton of the Utah Jazz. Just kidding. I wonder if there is an archive.org version of stuff on BICS. Moving on, though, past this Maxwell mini floppy disk, really, mini, MD2 HD. Okay, so moving past that advertisement, is this, sometimes it's not always clear if it's an advertisement or not, so I might read these a few more times. We'll see how far this series goes. It says, Smart Term, the next evolutionary step in communication software. In the world of communications, the result of natural selection isn't always terminal. All right, good job, writer or creator of this ad, not putting the, not correctly using punctuation with quotes. If they're more of a programmer than writer, though, obviously that could be forgiven. You can access your mini computer using standard terminals, but the smarter alternative is an IBM compatible PC and SmartTerm terminal. SmartTerm is an emulation software, an advanced species of communication software. Oh man, so they're really trying to go with this terminal and natural selection themed joke. Persoft begin where most terminal emulation software companies strive to end, with exact feature-for-feature emulation. Then Persoft took SmartTerm software to the next stage of evolution, superiority. SmartTerm 240, the latest in SmartTerm series, not only provides the Regis and the Tektronix graphics capabilities of a DEC V2-240 terminal, but adds capabilities that are only possible through the power of a PC. Features like error-free data transfer using Kermit or XMODEM protocols. I need to write those down for future research. So these features allow error-free data transfer and programmable soft keys. And now with the new add-on Network Kit, you can communicate through several popular networks. And if you're watching a video of somebody reading or reading through a magazine, you'll probably want the text a bit larger so you can pause and read it yourself if you want to. The strategy I'm going with here is just reading the first and last paragraph of many of these things. Maybe I'll read stuff in bold, but that's it. So it's December 2021 as of this recording, and it's crazy to read about lipid membranes as electronic components. Ultra-small memory with low power requirements. And I say this because we have these COVID vaccines that use mRNA technology, which basically means nanoparticles in a lipid, and that is the vaccine that is injected. So what do they have to say about lipid membranes? Two sciologists have come up with a way to use lipid membranes as electronic components. I wonder if Olaf Anderson is as of Cornell Medical Center and Robert Mueller of the State University of New York Health Sciences. I wonder if these two guys are still around to read and learn about this technology. Well, the article here, though, is saying that they claim that memory elements based on this technology can be extremely small and function under very low power requirements. Skip to the very end. Theoretically, you could use this technique to create wires measuring only 70 to 80 angstroms in diameter. And that's that nano realm I was just talking about. Over here, nanobytes, all of this stuff Just so coincidental. A report from Dataquest, San Jose, on the international semiconductor market in 1986 showed 3 Japanese firms at the top of the list, based on revenues. That is, so we got NIC, Hitachi, and Toshiba. This research firm, Dataquest, wonder if they're still around, said this is the first time a U.S. company hasn't been among the reigning trio. The remaining top suppliers were in order: Motorola, Texas Instruments, Philips, Signitex? I don't know how to say that. Signet? Whatever. So Fujitsu, Matsushita, and Mitsubishi. Of course, Intel is an easy one. Alright, moving on to the next part. New modulation method could pack more data onto disks. Company says it plans drive. Jeez, it's not the best title, subtitle duo there. So a new modulation method promises more information on computer disks, better audio recording, and more efficient communications, according to its inventors. Called Harmonic Modulation, the method is being developed by Adele Inc., which is in Tucson, Arizona. Thus, a 1 kilohertz signal can transmit 6,000 bits of information per second. Most modulation systems can transmit much less information on a 1 kilohertz channel. The microbytes continues on to page 10 here. They wrap up that section on the Tucson company by saying those guys are planning to build a disk drive using harmonic modulation by the second quarter of this year. And this is kind of hard to read. The nanobytes continues over here. Let's scan it for anything interesting. The Farmers Software Exchange in Fort Collins is a users association organized to help farmers and ranchers. The group offers at a discount programs geared towards agricultural operations, as well as word processing and database packages. That's kind of cool to me. One of my favorite classes of all time was agricultural economics. Warp speed, Mr. Sulu. Experimental computer calculates 100 MIPS and drives a car, too. So MIPS, this isn't merit-based incentive payment system. They're probably talking about MIPS architecture here. This stands for microprocessor without interlocked pipeline stages. So at this time, it was an experimental parallel processing computer developed at Carnegie Mellon. It has proved capable of, among other things, intelligently driving a car. So talk about overhyping things. We'll jump down to here. The company called Warp, short for Warp Speed from Star Trek, gets its nickname not from the speed at which it travels, which is about 1 mile per hour, but from the speed at which it calculates. According to Professor Kung, the computer makes more than 100 million calculations per minute. They say the Warp computer uses 10 Waytech floating point processors working in parallel to achieve such amazing high performance, which Kung said is about 100 times faster than a normal computer. And so Waytech is, or was, I should say, an American chip design company. According to this very reliable Wikipedia source, just kidding, it was defunct in 1996. I'm such a Google Images guy. Check this out. And after reading into Waytech a little bit, I'm a little nervous. I've misled you with this MIPS comment. I don't know what MIPS could be for other than architecture. Unless I'm blind, I don't see anything in this small article, the microbyte article, explaining MIPS in that sense. Well, here Philips shows CD-1 or -I images. That's why Ubuntu font is my favorite, because it disambiguates the number 1 and I. I'm going to assume it's I here. So CDI. Some oppose closed architectures, others plan products. So at a recent conference sponsored by the Institute for Graphic Communication, which is in Boston, Philips International showed for the first time to the public a videotape of CDI, Compact Disc Interactive. Definitely thinking I was the right choice there. Images generated by prototype hardware. The tape demonstrated the technology's ability to handle several different types of video. So yeah, we are talking about a Byte issue released in 1987 here. Let me try to flip between those two types of views. Here we have a nice Vintel modems ad. The rest of the microbyte articles is about Seagate to start building 3.5-inch hard disk drives. There's a company proposes format standard for optical discs, and researchers use ICs to repair severed nerves. Interesting. A more medical related thing here. They say because there are more than 2,000 individual axons, which is the nerve fibers that make up the nerve, because there's more than 2,000 of those fibers, it is virtually impossible to reconnect them using microsurgery. Consequently, signals to and from the brain cannot correctly get past the reattached nerve union once a severed nerve is sewn back together. This reminds me of the Neuralink stuff Elon Musk is doing. And sure, it's not actually him doing it, I get that. He is not his company's. They say the most difficult part of the process has been precisely laser drilling the 8-micron diameter holes into the 1mm by 1.5mm silicon chips. Grosser says that once they get a genuine direct access to the peripheral nervous system, there's no end to what can be accomplished. Wow. Is that dystopian or utopian? Again, we're in December 2021, so I'm more on the dystopian side of things. We have this ad, why does Chrysler use Telenetics modems in its data networks? God, I love the artwork of these things. And our first long article of the magazine, titled The RISC-CISC Melting Pot, Classic Design Methods Converge in the MC6830 Microprocessor. And this is by Thomas Johnson. Tommy John. Just kidding. Comparisons of the relative architectural merits of the reduced instruction set computer and complex instruction set computer methods might prove to be one of the more interesting computer science debates of the late 1980s. However, these two seemingly disparate views of the correct way to build microprocessors might not be as far apart as they seem. This article examines the Motorola 6830 microprocessor with respect to the RISC-like features in its classic CISC machine. Before delving into the MC6830's innards, I will encapsulate the RISC and CISC strategies. The term RISC is somewhat of a misnomer. The acronym has two commonly accepted meanings. The older meaning is reduced instruction set of computer, and the newer is reusable instruction set. I've never heard of the reusable version of that definition. Both names imply that RISC has something to do with optimizing the microprocessor's instruction set. While this is true, it is also misleading since RISC is much more than simply an architecture that necessitates a smaller or more efficient instruction set. Likewise, CISC is more than just an architecture that embodies complex or high semantic content instructions. That's a nice way of saying verbose, isn't it? No, don't talk trash to me. I understand it's not verbosity if it has purpose, whatever. The tenets of RISC. The major tenet of RISC is the investigation of the assignment of system functionality within its architecture. RISC strategies normally lead to the offloading of the more complex or infrequently used instructions onto the compiler. I think that's an important differentiation there. So I wonder if it's fair for me to summarize it like that. RISC offloads complexity to the compiler, makes a compiler do a lot more work. And we're skipping around, so if you wanted to read the article in its entirety, just click the link in the description here. Single cycle operation for every instruction. In order to operate in a single cycle, an instruction set or an instruction must be either relatively simple or backed up by additional hardware logic. Whether simple or not, single-cycle instructions yield rates of many millions of instructions per second. High MIPS rate, millions of instructions per second. That's what MIPS mean in the context of the microbytes article. So I feel a little foolish, but I don't think MIPS is a common term, at least not in my experience. So they end this paragraph with an analogy, but TLDR is single cycle operations are nice. They talk about load store design. This point dictates that only load and store operations should reference external memory. This tenet lets all other implemented instructions follow the criterion of single cycle operations, since they will then have to operate only on chip registers. Memory references can be indeterminate in length of time due to normal memory access delays such as refresh and direct memory access controllers. And so I wonder, how much would you say things have changed since 1987 in that regard? Well, hardwired control, they're talking about micro-coded architectures have variable length instruction size and execution time. In a CISC machine, microcode is a highly desirable trait because it lets the designer implement many flexible, complex, so high semantic content, instructions, and addressing modes in minimal silicon real estate. In a RISC machine, however, microcode is less desirable. Microcode doesn't lend itself to single-cycle operations as directly as dedicated hardware logic. And this is because the microprocessor's hardware has to dynamically interpret the microcode. So relatively few instructions and addressing modes. They talk about fixed instruction format, more compile time efforts. The author here, Thomas Johnson, looks like he works for Motorola. So what a great person to write about Motorola, right? I think he'll finish his talk about the general CISC and RISC differences by addressing minimal pipelining. Pipelining in a CISC machine allows more efficient use of the available bus bandwidth and lets it produce performance equivalent to RISC architecture. The combination of these tenets allows the design of a processor using minimal design time and silicon area, but requires a very complex compiler. The designer can then put these silicon savings to advantage by implementing a number of helpful features, such as overlapping register sets, called multiple register sets, greater than 100 registers. This is not unusual for RISC machines. There's special hardware, like barrel shifters, floating hardware, cache memories, hardware multipliers, or special functionality interprocess communication hardware. Alright, so I'll summarize that part by saying these are considerations process designers have to think about. Now, a machine with a reduced or simplified instruction set does not necessarily have a crippled instruction set. Due to the massive numbers of on-chip registers, most program variables needed by a given procedure will be kept in the machine. Most variables kept in the machine. And then Thomas will provide an example there. CISC performance. CISC computers attempt to squeeze the most performance out of any given architecture. Since designers can make internal microcode execute much faster than external instructions, the overriding concern of a CISC implementation is to build into the processor high semantic content instructions, where such instructions are useful, and that reduced the number of external instructions that the microprocessor must fetch. Alright, so keyword right there. Keeping down fetches. Microcode allows the inclusion of many varied addressing modes. Anyone who's read the x86 Intel Programmer's Manual understands this concept of modes. And it looks like he's going to address the MC6830 specifically now. Now I went on YouTube to make sure I'm pronouncing that chip correctly, this 6830 or 030 or 6830. I didn't find many good videos on the pronunciation. All I found is a lot of videos of old games being ran on this chip. So it's really interesting. I suggest you type that into YouTube yourself. Back to the magazine though, that's a pretty nice graphic. I'll take a screenshot of this and tweet it out. And same with this one below. Thomas writes, suffice it to say that a cache memory is a fast access, relative to the main memory system of course, fast access local memory where copies are kept of the most recently accessed main memory locations, along with some bookkeeping data. And I have other videos on the von Neumann bottleneck. They talk about DMA processors here, direct memory access ones. Maybe I incorrectly jumped around though. The ad screwed me up, that's my excuse. I was supposed to start over here, so do not attempt to limit the compiler to load store architectures. However, they do incorporate many high-level constructs to assist high-level language compiler writers. Due to the circuit complexity that results from CISC implementations, much more time is normally involved in the design debugging of the processor, and much more care must be taken to ensure proper operation at high clock rates. So now they specifically address the von Neumann bottleneck. I'm going to skip over here. This Motorola chip builds upon the architecture born in 1979 with the release of the MC68000. For a complete discussion on this, go ahead and read this other article. He says this was in the 1986 September Byte issue. While each of the M68000 microprocessors is based on the same CISC architecture, each has one very RISC-like feature, a large undedicated full-width register complement. So more graphics down here, program counter, address registers, data registers. In addition to the register set, the M68000 series has specific hardware designed to make the processor execute instructions as efficiently as possible. And look at that, they got a master stack pointer. Many of the MC68030's features are those you might expect to find only in RISC machines. Working in conjunction with the 2-cycle EU is the unique 2-level microcode structure, which is perhaps the single most non-RISC feature. That's a good retro computing trivia question to ask. Alright, so simply put, if you were to slice this chip horizontally across the die, you could consider the upper half the microstores, which is a software interpreter, and the lower half the EU caches, etc. A RISC engine. So see figure 7, figure 6, 5. Alright, here's figure 7. The location on the chip of the various circuits. So bus control, EU, execution unit, data cache, D-tags, nano ROM. Making me think of Star Trek again. This chip features a 256-byte data cache to complement the 256-byte instruction cache. Okay, so I think that's enough for this article. Just to read the subtitles, Harvard architecture. They talk about that 3-stage pipeline, on-chip hardware for instruction support. Scrolling past the ads, here's the conclusion. I think it's a good conclusion to say it'd be a serious mistake to assume that the acronym RISC stands for high performance compared to CISC. And sure, that's a battle that is still being waged to this day. All right, let's switch to this view. Look at that COBOL ad. And I think the video has gone on long enough, so I'll do a part 2 of this particular issue, and I'll start reading about the Fairchild Clipper. As promised, the magazine's title talked about instruction set, so yes, here's some more instruction set stuff for us to read about.